Hello. So what I'm gonna do in this video is looking at the graphics of the latest consoles, which at the time is the PlayStation 5 and the Xbox Series X. So what I want to do first of all is just sort of compare those latest console GPU architectures. So the PlayStation 5, actually, it's the GPU. GPU. So you've got more than one processor in a modern system. Even your mobile phone that you probably have actually has more than one processor. So we've got the CPU, the central processing unit, that does all the general executions. It will, it will run your code, the software, that way. Sort of, we're used to thinking about as software. Now, the GPU is a graphical processing unit. So this is separate to the CPU, and its job is just to do graphics, or traditionally it's to do with graphics. We can use it for some specialist sort of generic work, but ultimately it's there to do all the pretty graphics and things that we want. Okay, so I'm comparing the GPUs here, so the graphics capabilities of the latest consoles. So we've got the PlayStation 5 here and the Xbox Series X on the right hand side. Now, the actual sort of clock speed, so this is how fast, every second, how many times can the PlayStation 5 do things. So, we're looking at over 2.2 gigahertz. So that's how many times per second. And the Xbox Series X is slightly lower. Okay. However, you'll see from most of the other things, the Xbox Series X actually wins out on other things. So we've got these things called shader units. We'll be looking at what a shader is, how fantastic they are, very shortly. But you can see that the Xbox Series X has a few more. Okay, well, it's almost 50% more. Okay, we're looking at 2,300 rather than 3,300. And also the compute units. Okay, so you can kind of think of these as processors. Okay, within the processor itself. So each of these might be running, well, the overall clock might be running lower, but we've got more of them on the Xbox Series X. And in fact, if you look at all of these together, then this processing power, these teraflops, these are a measure of how much work a GPU can do, okay, each second. So you can see that the Xbox Series X actually wins slightly out on the PlayStation 5 on paper. Okay, in reality, tests have shown that they're very, very similar. And in fact, the PlayStation 5 can win out on certain situations, probably just down to this slightly higher clock speed, but we'll see. But as you'll notice, they're actually built on the same architecture. Okay, so they're both running AMD GPUs. They're slightly different from each other, but they're based on the same framework, the actual hardware architecture. And as you can see, they can both output up to 4K, 120 hertz. So what is nice is this new bit over here. So traditionally, we've had this, what we call a rasterized pipeline. This is where we create lots of triangles and we get the GPU to move them around and color them. Okay, now a number of these have been around for quite some time, and I'm going to go through some of the important parts of here, particularly vertex shader, the tessellation, and the fragment shader, because they're still used in an awful lot of games and so on. But what we have introduced with the latest consoles is this idea of ray tracing, and it's completely different to the traditional sort of graphics pipeline, and it allows us to simulate the way that light bounces and reflects and refracts off real surfaces, all in real time, all in a video game. So this is really, really exciting now. So I mentioned vertex shader. Well, a vertex is where two edges meet. Okay, so we've got two edges that meet at this point. We've got these two edges that meet there, and we've got these two edges that meet here. Thus, every triangle has three vertices. Okay, so you can think of them as the corner of your triangles. Now, this is interesting. So I said that everything with a shader, okay, it is very interesting, and it's because it's programmable. What that means is we can write our own code that runs directly on the GPU to override the default functionality of this particular stage. Okay, that's fantastic. Okay, I remember having to go out and buy a particular graphics card because it had some special effect that your latest game required. Okay, that went a long time ago now, where we get more and more processing power for vertex shaders, but ultimately we can write our own code to do our own special effects, and this is fantastic. So anything with the word shader in there means that we can override the default code that's in there, so we can write our own code and make it do whatever we want to. And one of the things that the vertex shader can do is we could create this triangle, we can submit this triangle to the GPU, but we can transform that triangle, we can manipulate it, we can move it, we can change its colors and all sorts of things. So as an example here, let's say I've submitted this blue triangle. Then what I can do is I can write some code to move all of those positions in my game. I can change the colors or even set the colors directly in the vertex shader. So I can write my own code to actually change or even set those colors. I can apply an image, what we call a texture, to that triangle. What we do have to do is to submit the positions of each of these vertices, but everything else can actually be created and changed and so on directly in the vertex shader. So what that allows us to do is things like this. Okay, so what I'm going to do is I'm just going to turn my camera off. So this is real time. Okay, this is running directly on my machine. Okay, so, and you can see this is just a static model, okay, of this elf girl's head and shoulders. Okay, so it's a static model. Okay, it's not an animation, it's not a video. Okay, it's just a static model, just one model here that's loaded in. Okay. Now what I can do with the vertex shader, so I've got code running directly on my GPU. And what that code's going to do is allow me to interact with it and move the vertices of the triangles around. So what I can do is move the vertices around her mouth. So I've just got a slider up here, moving numbers from 0 to 1. And my code, when it gets that, that's running on the GPU for the vertex shader, when it gets that number, it moves some of the vertices accordingly. And we notice that her eyes are slightly sort of narrowing as well. I can make it much bigger. I can make her look a little bit sad by moving the brow up, okay, and sort of turning down the corners of her mouth. This is not an animation, as I say, this is one static model. But what I'm doing is I've got code that I can interact with and do things. Okay, so I can open her mouth. Oh, okay, I can sort of open her eyes. You know, there's a whole thing. I can make a sort of smirk, sort of squint, and so on, and do lots of things. Now, if I switch on this animate, what that's going to do is it's not an animation. It's just going to cycle through all. There's lots and lots of different groups that do all sorts of things, from lifting brows and that type of thing. So what I'm going to do is, if I just press this, this will cycle through lots and lots of all the different groups. It moves them around, so you can kind of see that this, how we can affect all the vertices in this this static model. So this is fantastic because it means we can submit this static model and get the GPU in real time to manipulate it. We can make it talk, we can give different expressions, and so on. Tessellation. This has been around a little while now. What this allows us to do is to take an existing polygon, for instance, a triangle, and we can split it up into smaller triangles. Why would you want to do that? Well, one of the benefits of this is displacement mapping. So I could take one big square, I can tessellate it into many, many, many small squares. And then if I use an image, a grayscale image, I can use the information in here, the colors, to move some of these up or down. So I can just start out with a square, one big square. I can tessellate it into smaller squares, and then I can move these new vertices up and down based on whether it's on this grayscale. So full white might be up, full black might be down, and mid gray might be somewhere in the middle. And I actually end up with something like this. The other thing the tessellator can do is vary the amount of tessellation happening. So actually, what I would have is I'd get a 3D artist, okay, excuse me, to create this handsome chap on the right here. And what would actually be outputted by their graphics software is this thing. Okay, very low resolution poly model, okay, with lots of displacement maps and lots of information, so that we can write code on the GPU, because the parts of the tessellation have shaders, so it means we can actually override that, the default functionality, so we can write our own if we want to turn this guy all the way through to this. So this is great because it means we only have to store this on disk. We only need to send this to the GPU, and the GPU can turn it all the way through to this. So to show you this, here's a demo. So this is running in real time. Okay. In fact, just let me move it down so you can see me as well. There we go. Okay. So yeah, let's just move along here. Okay. So as you can see, yeah, we've got this sort of environment, this game environment. This looks okay, but hopefully you can see this geometry. This is what's been sent to the GPU, and you can see that this is flat. You can see that from the shadows. Okay. And this wall, all of this is flat. Okay. Now this is what's been sent to our GPU. Now, if I turn on the code running on the tessellator, this is what we end up with. What you can see here is, if I turn it off, this is what's been submitted. It's flat. In fact, you can see there's a line here. Okay, you might be able to see there's actually a line there between the sort of the textures. So these are flat. Now what we can do is tell the tessellator, actually, I want you to turn all of these into actual cobbles. And these are now three-dimensional shapes that have been created by the GPU. Okay, we need to tell it how to do this, but you can see from the shadow, these are actually there now, they're real. But it wasn't being sent, the GPU is creating these in real time for us. And you can really see that with these steps. So, you know, this is flat, this is one big thing here, but actually, let's just create these stones, and we've got all these stones actually happening in here too. So if we just cycle through, let me turn it off, let me come back, let's go to our dragon. Okay, so let's just bring this chap down. So what is nice, okay, so this is what's been sent to the geometry, into the geometry being sent to the GPU. But if I turn on the tessellator, you can see that all these spikes have been added to the dragon, and obviously all these stones and everything, all the walls, all's been done. So there's a lot. And this doesn't look too bad, but it means we can add all of these spikes. So what we are doing is by only having this sort of quite low resolution model, it looks pretty good anyway. It means we can run this same, if this was a game, this is actually just a graphics demo, but if this game was running on hardware that would struggle with or doesn't have tessellation on it, we can still play the game. But it means that if we do have a tessellator, we can turn that on and get better graphics, but it's ultimately the same game. Now, the fragment shader, this has been around a long time. What this is a shader, so it's programmable, so it means that we can, we can do our own thing with this. Okay, we can make it do what we want, but it's all to do with coloring that final pixel on the screen. Okay, so every single pixel we can actually figure out what that color should be. So we can do our things like lighting, we can add textures, so images to our triangles or fragments. We can do reflection, refraction, and things like that. Okay, so just to show you this, so again, it's not video, this is running straight on my machine. Okay, now what I do have, just to look around, this is basically a big box we're in. Okay, it's a big cube that we've pre-rendered, sort of taken photographs of a room, and we've applied it to this box. So it's just a box. Okay, it's fake, it's not a big room, it's just a box. And what we can do is use the fragment shader to fake, and it is real fake, this is not ray tracing yet, to sort of fake it so it looks quite nice. But as you can see, there's some lights around, and so we can get the lighting to work really well. I've got some refraction, so there's a billboard behind here. So if I place this here, what this is doing is I'm firing a sort of pretend ray, and it's this ray casting, and a ray sort of comes out of the bunny, and we see where it hits our big box. Okay, so it's only the box it's going to interact with. So if we had other objects in here, they wouldn't be hit by that ray. This is not ray tracing. Okay, but as you can see, it looks quite nice, and this capability has been around on smartphones well, pretty much since smartphones were actually invented. But as you can see, we can get some really nice effects on this. So that brings us nicely to the new kid on the block, okay, ray tracing. So what is ray tracing? Well, what we can do is, let's say we've got this object and we want to see it on the screen. We can fire rays, okay, from the camera, pretty much for each of these pixels on the screen. And it might hit. But instead of coloring that particular pixel green, we can fire off rays. This is ray tracing. We're going to trace where all these rays have come from. So maybe it's hit this. So maybe we combine, or we can see part of that red in this green thing. So we start to have these things bouncing around. But what we can do is add more and more rays, okay, to make it more and more realistic, because surfaces aren't purely smooth. Okay, even a mirror has slight bumps in it, so we can actually fire off more. So the more rays we fire off from that particular position, the more accurate and the more lifelike colors and things can be. But interestingly, the ray tracing capabilities of the consoles have been used for more than just sort of graphics work. What they're also being used for are things like audio. If you think about audio, audio can bounce off things. If you're in a cave, then it'll echo and so on. So actually, they can be used for ray tracing. So let's just look at this little demo. This is actually by NVIDIA rather than AMD, but this is a really nice demo showing the same graphics capabilities as the consoles. So when you see that this is on, this is the ray tracing is turned on, and when this goes off, you'll be able to see the difference in this.
So what's really amazing is notice how crisp this is.
Oops, let me just turn myself off.
This can't be a video. This is in real time. Look at this. Everything is in real time. And RTX on, RTX off. Notice the reflections were all broken. And the reason for that is because screen space doesn't allow us to reflect what is behind the object. Notice the soft shadows. The soft shadows result because of an area light. The combination of umbra and penumbra causes the soft shadows to look so exquisite. And that just happens with ray tracing. No shadow maps necessary. There's an area light just underneath this robot, and it's interacting with the light, and it's combined with the light of the head, all being spun in real time. There's a reflection of a curved surface. Reflecting off of a curved surface is super hard to do, really hard to fake. And screen space reflection simply breaks. There's another scene. Reflection and refraction.
Okay, so what we can do is start to put all of this together.
It has to be the right way.
Before we continue, let's stop a moment and take a look at some of the key features of this demo. Much of what you see was built with Quixel Megascan assets, but instead of using the game versions, we used the cinematic versions, which would typically only be used in film. There are around 1 million triangles each, and thanks to virtual texturing, they all use 8K textures as well. Nanite can render an insane number of triangles very quickly. There are over 1 billion triangles of source geometry in each frame that Nanite crunches down losslessly to around 20 million drawn triangles. What does that many triangles look like? This isn't noise. These are the triangles, each a different color. Most are so small that they look like noise. Nanite achieves detail down to the pixel, which means triangles are often the size of pixels. This amount of geometric detail requires shadows to be pixel accurate as well, and Nanite can do that too. Speaking of lighting, all of the lighting in this demo is completely dynamic, with the power of Lumen that even includes multi-bounce global illumination. No light maps, no baking here. Without GI, all of that beautiful lighting is gone. With Lumen enabled, we can move the light and the bounce changes instantly.
Okay, so hopefully you've enjoyed this sort of talk, this video. Okay, so yeah, the biggest thing now in the latest consoles is ray tracing. It's yet to, at this when I recorded this, it's been used in 1 or 2 games, but I think as we just saw there, particularly in that Unreal engine. So this is an engine that's available to lots and lots of different game developers. That was running in real time. So yeah, the future's looking very, very good for games. So if you'd like to know more, then please contact me at d.mckay@hull.ac.uk. Thank you.